Good evening to the participants.
Good evening, sir.
Yeah, uh, so thank you for joining. We will start the session as usual at around 7:10. We will wait for the participants to join. Good evening. Hello.
Yes, everyone.
Yes, I hope that my voice is audible.
Yes, sir.
Hello. Yeah, thanks for confirming. So, I we'll start the session right now. So, I welcome you all to this live interaction session number 4. This course is brought to you by NPTEL, and the title of the course is, as you might be knowing, Advanced Reinforced Concrete Design, and the course is being instructed by Professor Surya Prakash from IIT Hyderabad, and this is the 4th session in our series of live interaction sessions, and this session is being presented by me. I'm S. Lalit Sagar. I'm a doctoral candidate and PMRA fellow in the Department of Civil Engineering at IIT Delhi. So I warmly welcome you all for this live interaction session, and I believe one of the participants is new. Would you like to briefly introduce yourself? Chinmay?
Yes, sir.
Yeah, yeah. Please go ahead if you would like to introduce yourself.
I'm Chinmay Malvankar from Malvan, and I'm currently pursuing a master's in structural engineering.
Okay, wonderful. So, where exactly you are doing your masters?
Uh, I'm doing master's from Sanjay Ghodawat University from Kolhapur.
Okay, okay, okay. Very nice to have you. I think you were not there in the initial first three lectures, I believe.
No, I was there. I was present on the first interactive session
Okay, okay,
and had some issues with network during the second and third interactive session,
okay, okay,
so I
okay.
could not attend it.
Right. So, I hope you are following the lectures so far, the weekly lectures.
Yes, I am following the lectures.
Yes, yes. So, you're able to solve the assignment problems?
Yes, sir.
Okay, okay. Okay, I hope you enjoy the session. We first the protocol of these live interaction session is that we will first start with the brief summary of the lecture slides that was taught by Professor Surya Prakash. We'll do that for about 5 to 10 minutes, and after that I have designed certain problems. There are 14 problems in this session, and I hope that we can learn the concepts uh, associated with the lecture content for this week. Okay, so I think we can start with the summary of the lecture slides, and after about 10 minutes we can go ahead with the problem solving. So if there is any issue with the audio or video, you can let me know, because I can switch you an alternate internet source so that we can go ahead with the session seamlessly. Okay, so first we are going to look at the summary of the lecture slides. So this was the fourth module, week 4 of the lecture, where we studied about the behavior of columns under pure axial loading. So in the first module we saw the introduction of reinforced concrete structures, and in the second module we discussed about the material properties. In the third module we looked at the durability aspects of reinforced concrete structures, and in the fourth module we'll be dealing with the behavior of column under pure axial loads. So from this lecture onwards we will be focusing more about the mechanical behavior of structural elements. So this week we are going to be dealing with axial loads, and in the next week we are going to be dealing with the flexural members, and so on. So these are the expected learning outcomes for this week. We are going to introduce the basic laws of mechanics in concrete behavior. We are going to explain the load deformation or the load displacement behavior under pure axial compressive and tensile loads. Then we are going to explain the role of concrete and steel in compression and tension, that is how they are going to take up the loads and deform when they are subjected to compressive and tensile loads. Then we are going to differentiate the behavior of columns when we use the normal strength concrete and the high strength concrete. So the reinforced concrete members, they are predominantly subjected to these four types of stress resultants, that is axial, that is compression or tension, or they can be subjected to flexure, that is bending, or they can be subjected to shear as you can see in the form of these lateral loads, or they can be subjected to torsion, that is twisting about the central axis. So the focus of this particular week's lecture and live interaction session is going to be the axial behavior. So we are going to essentially consider column, and we are going to develop the force deformation relationship when they are subjected to either compressive or tensile load, and we are going to combine. Okay, moving on. So we have the moment resisting frame, as we can see here. So the horizontal members are the beams and the vertical members are the columns, and the beams are generally subjected to flexural shear and torsional loads, and the columns are subjected to axial loads, flexural loads, shear, and sometimes torsion. And then we have these bracings. So can anybody explain what is the role of bracings here?
Stiffness works.
Yes,
To prevent lateral swaying of the frames.
yes, exactly. Both the answers are, exactly right. So first we are going to provide the bracing so as to ensure a higher stiffness of the structures, and whenever there is a lateral load in the form of earthquake or wind, it can sway in the horizontal direction. So in order to impart stiffness, we introduce bracings. So these bracings, uh, generally they are provided with the pin support, pin joint at the end, at either ends. So they're usually made to undergo either pure compression or tension. So for example, in this tie arch bridge, so these vertical members are subjected to either tension or compression. Okay, so whenever we consider a column, there can be a combination of axial, flexural, shear and torsion, but for this particular uh, module we are going to study only the axial behavior. Okay, and in the subsequent modules we are going to increase the complexity of the mechanics problem, where we are going to introduce the flexural load, we are going to introduce the shear load, but for this particular module we are going to confine ourselves only to the axial loading. Okay, moving forward. So here we have a column made of concrete that is reinforced with steel. So the behavior of this reinforced column can be likened to that of two springs that are connected in parallel. So these springs, they're having a parallel configuration, and consider that there are two rigid plates. So whenever we are going to apply a uniform compressive or a tensile load in this case, so both these springs undergo equal amount of deformation, equal amount of axial deformation. However, the force is going to depend on the stiffness of each of these springs. So we are going to solve the problem by using two basic principles of mechanics. We have the equilibrium of internal forces, that is, the external load applied P is the sum of the internal load or the internal resistance provided by the concrete and steel. Okay, so that is what this particular equation signifies. External load P is equal to resistance provided by concrete plus the resistance provided by steel. Okay, and then the second principle is the principle of strain compatibility. So we are going to assume that both these springs are going to deform by the same amount axially. So that is elongation delta L is equal to delta LC is equal to delta LS. That is, elongation in concrete is assumed to be same as the elongation in steel bars. So the total load on the column is expressed in terms of the area of concrete and the the stress in concrete, and then the area of steel and the stress in steel. Okay, so whenever the deformations are within the linear range, that is, if we consider the stress strain behavior, if excuse me, I'm going to try to explain this with some okay. So I'm going to briefly explain this phenomenon. So basically we are discussing about the column. So we are going to subject it to compressive load. Let's say it is P1, and so this corresponds to the stress strain curve of concrete. Okay, so there is a linear portion, before this point. Let's call it epsilon 1. So as long as the stresses are within this strain value, the strain is within the value of epsilon 1, it behaves in a linear fashion. In that case, this particular equation holds good. P is equal to AC into EC plus AS into ES, and epsilon is still in the it is still in the linear zone. It is still in this linear part of the curve. However, when the column goes into the nonlinear zone, that is, the strain enters this curved or the nonlinear part, then usually the calculations are a little more involved, and we are going to express this stress in concrete as a function of strain. Okay, so first we are going to determine the we are going to pick a value of strain, and then corresponding we are going to determine the value of stress, and then when we multiply that with the area of concrete, then corresponding calculation when we do for steel, we ultimately get the value of P, that is the axial load within the column. Okay, so in order to characterize the stress strain behavior, we have the parabolic law or the Hocknestad law for concrete, and then for steel we are going to assume a bilinear relation. We are going to assume that up until the value of this Fy, it is going to have a linear relation, and then it is going to plateau. It is going to remain constant at around 500 MPa. Okay, and this relation is going to be same for compression and tension. And for concrete, however, we have this limit on the tensile capacity. We are going to be discussing more about these concepts in the form of numericals. In fact, 90% of the class today is going to be based on numericals only. Okay, then we have for plain concrete, the behavior of plain concrete varies from the reinforced concrete. So upon reaching the maximum tensile load, the column ruptures. However, when we consider a reinforced concrete column, so it has multiple stages. So first it is going to experience cracking. So up until the point of cracking, all the load is entirely resisted by concrete, but once the concrete ruptures, the load is going to be taken up entirely by steel, signified by this part of the curve, and then once the steel also undergoes yielding, then it is going to have a yielding profile. Okay, so we are going to analyze the members for axial behavior. So what we mean by analysis is that we are going to develop force deformation curves. So this is the algorithm that you are going to follow. So in order to develop the force deformation curve, so if we take if we take any axial member, okay, so the y-axis is defined by the force and the x-axis is defined by the deformation delta. So what we are going to do is we are going to pick different values of strains, and then we are going to plot the behavior on the compression side, and then we are going to plot the behavior on the tension side. Okay, so this is what we are going to we intend to achieve in this particular class. So the algorithm is that we are going to we are going to choose a value of concrete strain, then we find the corresponding strain in steel through compatibility, and then we are going to determine the stresses in concrete and steel through the constitutive model, whether it is the Hognestad relation or the Thornfield relation for concrete or the stress strain relation for steel. Then we are going to calculate the corresponding load through the equilibrium equation, and then we are going to determine the axial deformation using the value of strain by multiplying the value of strain with the length of the member. So in the lecture of Professor Surya Prakash, so he started with the behavior of a plain concrete column. So then we developed the force deformation curve. Yeah, so this is how it looks like for a plain concrete column in the compressive side and on the tensile side, and then we looked at how the behavior changes when we are going to introduce these steel rebars. Okay, so when we introduce the steel rebars, you know, the compressive and the tensile behavior varies considerably. So okay, so here is a comparison. So both the compressive and the tensile capacity of the column improves significantly. Then for the third problem, we replaced the normal strength concrete with high strength concrete, and then with the same reinforcement we tried to evaluate what would be the change in the axial behavior, and correspondingly after several calculations we developed the load deformation curve. So basically in this live interaction session we are going to take up certain theoretical and numerical problems. So I hope all of you are with me. If everyone is ready, we can go ahead with the live interaction session. I hope that my screen is visible now.
Yes, sir.
Yes, sir.
Yeah. Today's class we are going to have 14 multiple choice questions. So as we have interacted in the previous 3 lectures also, I hope that we can have a nice interaction session and make it mutually a very good learning experience. Okay, so this is the first question. The load bearing capacity of a reinforced concrete axial member depends on which of the following factors? So this has to be under axial loads, depends on which of the following factors. So there are multiple options for this particular question.
ABCD.
Okay. Okay, thank you for the response. Anybody else would like to contribute?
ABCD.
Okay. Okay, so since it is a straightforward question, let's not waste any time and yeah, so the correct answers are A, B, C, D because the explanation is that the axial capacity is given by this equation AC into FC plus AS into FS, where AC corresponds to the area of concrete, F is the stress in concrete, AS is the area in steel and Fs is the stress in steel. Okay, and the contribution of transverse reinforcement is ignored while we determine the axial load bearing capacity of RC members. Okay, so moving on to the next question. So we're going to start with the numerical straight away, and I hope that you have solved the numerical problem that was discussed in this week's lecture. So consider a square plain concrete column of side 300 mm and the concrete has a mean cylinder strength of 30 MPa. If the length of the column is 1 meter, what would be the force in the column corresponding to concrete strains of 0.001, 0.002 and 0.003? Okay, I hope that all the data is clear. So you can take 2 minutes and you can let me know the answers. I hope that everyone is trying to solve the problem. So today's class will be 90% numericals based. This week we'll be discussing the axial members, and we're going to be taking up other load actions such as flexure, shear in the subsequent lectures.
Answer is D, sir.
Okay. Okay, thank you for the response. Anybody else would like to try and give the answer?
Answer D.
Okay, thank you for the answer. So we can wait for another 1 minute and then we can see the correct answer and the solution for that. Right, so as the participants answered, the correct answer is D. I'm happy that you got the answers correct. So yeah, I would like to go ahead and solve the problem for you. Yes, so I would like to outline the steps first. So the step number 1 is that we have the value of epsilon c that is given. Okay, the value of strain we have, so from that we need to find out the value of the value of stress, that is Fc, and from that we need to find out the axial load. So it is quite straightforward, and the constitutive relation is governed by this particular parabolic law or the Hognestad stress strain curve. Okay, so for epsilon is equal to 0.001, when we plug the value of epsilon here, we know that the value of F prime C, that is the concrete cylinder strength, is 30 MPa. Sorry, and we are going to assume the value of the peak strain, that is epsilon prime C. Epsilon prime C is 0.002. Okay, so for case number 1, we are solving the first part of the problem. We have Fc is equal to F prime C, that is 30 into 0.001 by 0.002, pardon me for my handwriting, minus 0.001 by, I'm sorry, we missed a 2 here, 0.002 whole square, should be a flower bracket. So when we solve this, we get the value of, can anybody volunteer the value, those who have solved the problem? So the value is 22.5 megapascal. Now the force in the concrete bar is given by P is equal to Fc into AC. So when you solve 22.5 into AC is nothing but the column that we have considered is 300 by 300 mm, right? Right, so this is nothing but 300 square, which gives us the answer of 2025 kilonewton. Okay, I hope that it is clear for those of us who didn't solve the problem earlier. Now if we do the same operation, okay, corresponding to epsilon is equal to 0.002, so one of the trick here is that you don't even need the parabolic law, because for epsilon, I'm sorry, we need to use the right notation, epsilon c. Here also it is epsilon c. So since epsilon prime c is 0.002, so epsilon c by epsilon prime c becomes 1, so 2 into 1 minus 1 square, 2 minus 1, that is 1, so fc is nothing but f prime c. So for this particular case we have fc, the stress in concrete is nothing but the mean strength of the concrete cylinder itself, that is 30 MPa, straightforward. So when we plug it in this particular equation, okay, P is equal to 30 into 300 square, so that gives us the value of 2700 kilonewton. Okay, and for the third case, let me change the color of the ink so that there is some contrast. Okay, so for the third case, epsilon c is equal to 0.003. Just substitute in this particular constitutive relation, and by the parabolic law the value of fc turns out to be the same as the first case, right? So fc is 22.5, and subsequently the value of b would be 2025 kilonewton. Okay, so that is why option D was the right answer, 2025, 2700 and 2025 kilonewton. Okay, so yeah, so we'll move on to the next question. So in this particular question we looked at the compressive behavior, and the next question we are looking at the same problem but the tensile behavior. For the square plain concrete column given in question 2, what is the cracking force and deformation under pure tensile loading? Okay, you can take 2 minutes, it is quite straightforward. We need to find out the value of cracking force and the axial deformation.
B. B for Bombay.
B for Bombay.
Yes, sir.
Okay, thank you for the response. Anybody else would like to add? Okay, we can take another 30 seconds. Then we will look at the answer and how to solve the problem. Okay, so the correct answer is B. I'm really glad that some of the participants are able to get the right answer. So for this particular problem, again we are considering the same column, that is 300 by 300 mm, and 300 by 300, and so we know that when concrete column is there, plain concrete column, when we apply tensile load, so it just breaks off at one particular point. Okay, so it forms crack, and that's it. So when we plot the the tensile behavior, it is going to just go there and drop off. Okay, so if we define PT as the cracking load, so PT is given by F FT FTC into AC. Okay, so generally the though the tensile strength varies from 8 to 15%, we can assume it as 10%. So this would be 0.1 into 30, that is the F prime C, that is the compressive strength of the concrete cylinder, into 300 square, that is the area of concrete. Right, solving, we get the value of 270 kilonewton. Okay, now how do we determine the value of the deformation? Okay, so as we know that the value of deformation is given by epsilon TC, that is the strain at which the concrete bar fractures, into the modulus, the length. Okay, the length of the concrete bar. So the length of the concrete bar is given as 1 meter. So we need to find out the value of epsilon TC. So epsilon TC is given by FTC into modulus of elasticity of concrete based on the stress strain constitutive relation. So as we know, the value of EC is nothing but 5000 into square root of FCK. Now how do you find out the value of FCK? So we have the sorry, I'm going to take a different color just to differentiate. better contrast. Okay, we have the value of f prime c as 30 MPa. So we need to convert this concrete cylinder strength to cube strength. So FCU is equal to 30 into 1.25, right? So we have 37.5 MPa. Now FCK is given by this FCU minus 1, I'm sorry, it has to be minus 1.65 times the standard deviation, right? So if we assume a value of 5 from the IS code, okay, FCK is 37.5 minus 1.65 into 5. Okay, this gives us the value of 29.25. Excuse me. So when you plug this value in this particular equation, we get the value of EC as, any one of the volunteers can, okay, that is 27041.63. Okay, so when we substitute back in this particular equation, we have epsilon TC is equal to FTC is nothing but 3 by this value EC. I'm going to just write EC. So we get a value of 0.00011. Okay, when you multiply that by 1000 mm, we ultimately get the value of delta is equal to 0.11 millimeter. Okay, so we have value 270 kilonewton and 0.11 mm. That is the right answer. Okay. So I hope that we are able to solve the problem. Okay, moving ahead, we will go to, sorry, okay, I hope that my screen is visible. So now the question is to combine the force deformation curve for question 2 and question 3. That is, we are going to combine the compressive and the tensile behavior. Okay, so I hope that my screen is visible.
Yes.
Yes. So basically I have used the results that we got from the question 2. So this, excuse me, I'm just going to highlight just for clarity. So this particular part of the curve, the positive one, so this was I plotted from question 2 and this from question 3. Okay, so you can just do a similar exercise with you. If you have you can just use Excel and you can plot it. So if anybody is interested, I have solved this using Excel, and I'll be happy to share this with you if you want to just Yeah, so I have done it for the different problems, right, that we're going to discuss in the class today. Okay, so moving on, we'll move on to the next question. So in the first question we looked at the axial behavior of a plain concrete bar. So for the next problem we are going to see how the behavior changes when you're going to introduce steel rebars. Okay, yes, so this is the question. Please read the question carefully. Consider a square concrete column of side 300 mm and length 1 meter. The concrete has a mean cylinder strength of 30 MPa as with the previous problem, and the column is reinforced with 4 steel rebars of 25 mm diameter. What would be the force in the column corresponding to concrete strains of 0.001, 002, 003 and 004? Assume Fy is equal to 500 MPa. Okay, you can take 4 minutes. Okay, then we are going to discuss the solution for this particular problem. I hope that all of you can try the problem, try to solve it. So for the behavior of concrete, you're going to be using the same parabolic law or the Hognestad law. The only new component is that we need to consider the stress in the steel reinforcement. So if you are able to...
Answer is C.
Okay, thank you for the response. First we need to determine the stresses in steel and concrete corresponding to the value of strain that is given. Then based on the law of force equilibrium, we can find out the value of forces in the column corresponding to the different strain values. The participants have 1 more minute to solve the problem. So anybody else would like to try?
Answer C.
Yeah, thank you for the response. So yeah, as the participants have mentioned, the correct answer is option C. Okay, thank you for the answers. So we'll be looking into the solution right now. So yes, so I'll draw the sketch of the cross section over here for reference. Right, so we have a square column. I hope that the participants are those who could not answer. I hope that they're noting down the steps. And we have 4 rebars, right, of 25 mm diameter. Right, so we have 4 bars of 25 diameter. So the first order of business is to find out the value of area of concrete and the steel rebars, right? So we have area of steel is yeah, pi by 4 into 25 square multiplied by 4. We have 1963.5 millimeter square, and AC would be 300 square minus AST. Okay, so that would give us a value of 88036.5 mm square, right? So for the first phase we need to find out the force in the column corresponding to a strain of 0.001. Okay, so we have the value of epsilon prime c as 0.002. So when we plug these two values in this particular equation, and the value of epsilon prime c is 30 MPa as usual in the previous, as we saw in the previous problem as well, we get a value of Fc as 22.5 MPa, right? Now the only change is that we need to determine what would be the value of stress in steel. Okay, that is Fs is given by epsilon s into Es. So by the principle of strain compatibility, we are going to take epsilon s as same as epsilon c. Okay, that is 0.001 into 2 into 10 to the power 5. So that gives us a value of 200 MPa, right? So simply by substituting that in the equilibrium equation, P is equal to Fc AC plus Fs into As. So we have the value of Fc, AC, Fs and As. We get a value of 2373. Yeah, 2373.5 kilonewton. Okay. Yes. So I think similarly, if we solve the problem corresponding to I think we'll try to accommodate the remaining answers here only, right? So since we have done the calculation for one value of epsilon c, we can proceed with the same procedure, with the same formula for the remaining ones as well. Okay, I will move ahead. You can always practice, and if there is any issue we can discuss in the next class also. So I'll call this P2 just to differentiate, P3 and P4. So the participants who have answered it, can you repeat the answer here?
3426.
Yes. Rounding off, we can write 34. I got it as 3426.5. And P3 we get a value of
2962.
yes, 2962. Thank you. 2962.6 kilonewton. So the participants can just note down these answers, and they can solve them and verify that they are also getting the same answers, right? And P4 is 981.8 kilonewton. Okay, so these are corresponding to epsilon c values of 0.002, 0.003 and 0.004. Okay, so we are going to plot the force deformation curve in subsequent slides, but before that there is a problem, and we would like to know, just like how we saw what is the load corresponding to different compressive strain values, what would be the cracking force corresponding to the pure tensile loading? What would be the cracking force and the corresponding deformation? So you can take 2 minutes, then we can look at the solution. I am very glad that some of the participants are answering, and we can get the most out of these sessions if there is better participation from all of you. We can try to solve any doubts if you have along the way. Yes, please take 2 minutes.
Answer C.
Okay, thank you for the response. Okay, so I think we can look at the answer now. And yes, as one of the participants said, the correct answer is option C, right? And again, it is quite straightforward. So the value of strain is same, right? Because first we need to determine the value of strain in the member, uh, because that is going to govern how much stress is there in the steel rebars, right? So first of all, we have FTC, that is the tensile stress in concrete is 0.1 F prime C, that is 3 MPa, right? So epsilon Tc is FTC by EC. So the modulus is same as in questions 2 and 3. So we have the value as 0.001 00011. Okay, now we need to find out the force, that is FC AC plus Fs into AS, right? So we know the value of AC, we know the value of FC, we know the value of AS. So in order to find out the value of Fs, so Fs is nothing but epsilon s into Es. So that would be 0.00011 into 2 into 10 to the 5, right? So we have the value as just 22 MPa, right? So when we substitute the value here, when we substitute the value of 3 into AC, I'm just going to mention the variable so that we can save some time. Fs 22 into AS, so that gives us a value of 307.3 kilonewton, right? And the value of deformation, delta is equal to epsilon into L, that is that is 0.00011 into 1000 millimeter. That gives us a value of 0.11 mm. So P is equal to 307 kilonewton and delta is 0.11 mm. So option C is the right answer. So we have the third part for this question. For the same RC column given in questions 5 and 6, what is the force and deformation at the point of yielding of steel reinforcement under pure tensile loading? So in the last part we looked at the force and deformation corresponding to the point of first crack. Now what would be the load and deformation corresponding to the yielding of steel reinforcement? Kindly take 2 minutes and come up with the right answer.
Answer A.
Okay, thank you for the quick answer. We will look at the solution in another 30 seconds. Yeah, so as one of the participants mentioned, the right answer is option A, and it is quite straightforward. So in order to as we were seeing in one of the previous slides in the summary, so when RC column is subjected to tensile load, so initially it will go like this up to the point of cracking in concrete, and after that it is going to be, the forces is going to be resisted by steel, and at the point at which the steel yields, the force is going to plateau. Okay, so we are looking at this behavior consisting of three parts. So the question was to identify the force corresponding to this particular point. If this is point 1, point 2, so basically we had to determine the force in the column at which the rebars yield. So that is given by P is equal to Fc into AC plus Fs into As. So Fc is 0 because after the bar has undergone cracking, the stresses won't be resisted by concrete anymore, into AC plus Fs, we are considering value of 500 MPa, that is the yield stress, and AS is 1963.5, which gives us a value of 981.75 kilonewton. Okay, and what would be the deformation? In order to find out the deformation, I'm going to solve it here. Excuse me. Okay, so in order to find out the deformation, it is straightforward. Epsilon s into L, and epsilon s is given by, we might be tempted to use the linear equation, but remember that we are dealing with HYSD bars. So the strain in steel at the point of yielding, this particular value is given by 0.87 Fy by Es plus 0.002, because remember we are finding out the value of this strain in steel using the 0.2% proof stress value. Okay, so when you substitute, you get 0.87 into 500 by 2 into 10 to the power 5 plus 0.002. Yes, epsilon s is equal to 0.00417. So delta is given by 0.00417 into 1000, which gives us a value of 4.17 mm. So thank you to the participant for the response, and the correct answer is 982 kilonewton and 4.17 mm. That is option A. So here what we are doing is we are just combining the force deformation curve for the different stages that we have analyzed. Question 5, that was the behavior of column under pure compression. Question 6 and 7 under pure tension. So this is what we get. So this particular part of the curve corresponds to the compressive behavior, and this corresponds to the tensile behavior, and this as you can see, this is a drop in the load, and this corresponds to the point when the forces are being transferred to from the concrete to steel. So there is a abrupt drop in the load, okay, and this is the point of cracking. Then after this point, the load is entirely taken by the steel. It is taking, and then ultimately at this point, corresponding to 982 kilonewton, the steel rebar yields, and then the force, the tensile capacity plateaus. Okay, so this is a comparison of the force deformation curve of the plain concrete column and the reinforced concrete column. Yeah, so at a strain, at a deformation corresponding to 4 mm, the plain concrete bar, the load capacity completely vanishes, but for the RC column, some residual force is still there, some residual axial strength is still there, and similarly, so both the compressive and tensile strengths are considerably increased when we consider when we add reinforcement to a plain concrete bar. Okay, so in this particular question, we looked at column with normal strength concrete. Now let us see a theoretical question. When a plain concrete column is reinforced with steel rebars, which of the following properties of the column does not vary significantly? You have 5 options.
C, sir.
Okay, thank you for the response. Anybody else would like to try?
Sir, C.
Yes, thank you for the response. Yeah, so we have one more big problem. So let us, without any further ado, we'll look at the answer. So the correct answer is C, as the participants rightly pointed out. So which of these properties does not vary? So that was the question. So when you add steel rebars, all the remaining properties do vary. The post cracking stiffness increases of the column, and the ultimate compressive strength of the column increases. Let us see here. So the post cracking stiffness, definitely it increases, and the compressive strength increases as indicated by the red curve. The tensile strength increases as shown by this red curve. However, the cracking load, that doesn't vary so much. Okay, so let us look at the value of cracking load. So the value of cracking load was 270 kilonewton for a plain concrete column, and for yeah, so
307.
yeah, it is 307. So it was, you know, hardly 10% increase. So in comparison to other properties, the initial cracking load was least affected, okay, or it didn't vary significantly. Okay, so we will move on to the next problem. Okay, yeah, so this is the, you know, again, stiffness increases, compressive capacity increases, tensile capacity increases, but there is no significant change in the cracking load. Okay, so we are going to look at a concrete column with high strength concrete, right? um, for the square concrete column of side 300 mm and length 1 meter, what would be the force in the column corresponding to the strains of 0.001, 002, 003 and 004, and here the mean cylinder strength is 65 MPa and the column is reinforced with 4 steel rebars of 32 mm diameter. So kindly solve this problem. You can take 5 minutes, and the main change to consider here is that in the previous problem we had considered the parabolic stress strain relation or the Hognestad relation, but here, since it is a high strength concrete, we need to consider the Thornfeld relation. Okay, so I request you to have a look at the lecture slides of week number 2 and week number 4 and try to solve this problem. Yes, so anybody was able to get the answer?
B, sir.
Okay. Okay, thank you for the response. Yes, anybody else would like to? If anybody else is trying, I can wait for another 1 minute, or else I'll go ahead with the solution. Okay, I hope I can go ahead right now. Okay, so as one of the participants mentioned, yes, the correct answer is indeed B. Thank you for the response. I'm glad that you were able to uh, uh, get the answer right. So here we need to be careful because I had given the problem with high strength concrete, so the stress strain behavior is different for this. So again, as we did with the previous exam questions, we had asked to determine the value of force corresponding to different strain values, that is epsilon c is equal to 0.001, 002, 003 and so on. Okay, so first thing we need to look is that we need to consider this two aspects. The value of k is different for two different parts of the curve. Okay, so for epsilon c values of 0.001 and 0.002, you have to take a value of k equal to 1. Okay, and then for 0.003, yeah, 0.003 and 0.004, based on this particular expression we can find out the value of k later. Okay, now in order to start the problem, first we need to find out the value of n, because in this constitutive relation, let me write it here, fc by f prime c is equal to n times epsilon c by epsilon prime c divided by n minus 1 into n minus 1 plus epsilon c by epsilon prime c raised to the power n into k. So first of all we start off by finding out the value of n. I'm going to write it in a different color so that we can obtain the values that are required in this particular equation and start plugging them in here. So value of n is given by 0.8. So while discussing in the live interaction session 2, I had requested you to make a modification in this particular formula. Okay, so it is not FCK, it has to be FCU, that is cube compressive strength, by 21.25. okay, substituting 0.8 plus 65 into 1.25 divided by 21.25 gives us a value of 4.62. okay, so when we plug it in this equation, for simplification, for 0.001 I'll take epsilon c by epsilon prime c as 0.5, right? So when we substitute in this equation, we get 65 into 4.62 into 0.5 divided by 3.62 into, I'm sorry, this has to be plus, excuse me, let me take the eraser. Yes, yeah, so we have 3.62 plus 0.5 to the power 4.62, because remember k is equal to 1. okay, so we get a value of Fc, that is how much? Yeah, so I am getting a value of 41. Yes, 41 MPa. okay, correspondingly let me make a table here. yeah, 0.002, 0.003, 0.004. so correspondingly pardon me, I have to accommodate all the values here. So let me take a different ink so that there is no confusion, right? So for this we get a value of 65 MPa, that is nothing but F prime C. Then corresponding to this we get a value of 15.73, right? And for 0.004 we have we can take it as 0 actually, right? And correspondingly when we substitute it in the equilibrium equation, that is P is equal to Fc into AC plus Fs into As. okay, and if this is the value of Fc, then we will also mention the value of Fs, right? Pardon me. okay, so the corresponding value of Fs would be for 0.002, that would be 400 MPa. This would be 500. Why? Because 0.003 into 2 into 10 to the 5, that would be 600, but you are going to cap off the yield stress at 500 MPa, right? So here also we get 500. Okay, ultimately we get, let us write down what would be the value of B for different values of epsilon c. Right. Okay, so corresponding to 0.001, we get P is equal to 4202 kilonewton. I hope the numbers are visible. Six nine 28 kilonewton. Then we have 2974. Ultimately we have 1609 kilonewton. Okay, I hope you are with me. I know it is bit mathematically rigorous, but I hope that you are able to follow what I am trying to explain over here, right? Okay, so moving on, what would be the cracking force and deformation under pure tensile loading? Okay, so this is a continuation of the previous problem. So I request all of you to attempt this problem and let me know the answer. I hope all of you are trying. So we will look at the solution in another 1 minute. So for the tensile behavior, it is more or less the same. There is no difference in the behavior of normal strength concrete and high strength concrete when it comes to the tensile behavior, right? Okay, so I think I'll go ahead with the solution. So the correct answer was option A, right? And again, the way to solve is quite similar to what we did with the normal strength concrete, right? So ultimately we need to find out the value of P. P is equal to FCT. We will write tension just to differentiate, plus Fs into As, right? So FCT is 0.1 into 65, right? So that is 6.5 MPa. Okay, and this is the tricky part. We need to find out the value of Fs. So how do you find out the value of Fs? Fs is given by epsilon s into As. Now we need to find out the value of epsilon s. Okay, so this particular epsilon s is given by epsilon s is equal to Fs by EC, modulus of elasticity of concrete. And for high strength concrete, the value of EC is given by this equation. EC is equal to WC power 1.5, that is the density, into 0.0385 into square root of FCU. So when you plug the values in this particular equation, 2400, that is the density of concrete, power 1.5 into 0.0385 into square root of 65 into 1.25, right? It's pretty straightforward. We get the value of modulus of elasticity as 40802.74 MPa, right? So let us take up a different pen now, ink to, so we have the value of epsilon s is equal to 6.5 by EC. So that will give us a value of 0.001. Oh, there are 3 zeros. 000159, right? So we get the value of Fs is equal to epsilon s into As. So I request you to just check with this value. We'll get a value of 31.8 MPa. Okay, and then ultimately when you plug it in this particular equation, you get value of P is equal to Yeah, let me write down 6.5 into sorry, AC in this particular case is 86,783 plus 31.8 into AS is 3217. So the answer is 666 kilonewton. Okay, and the corresponding deformation is 0.159 mm. Okay, yeah, so the correct answer was option A. Okay, I hope that you were able to follow the calculations, right?
Yes, sir.
Yeah, thanks for bearing with me. I know that it is quite mathematically intensive, but uh, you know it is something that we need to follow. I hope that you were able to follow all the steps that I followed, right? So yeah, we have one last numerical question. Okay, because after this it is going to be just a discussion of the force deformation curve. So I request all of you to just quickly solve this problem. It is very straightforward. You have to find out the force and deformation in the column corresponding to the point of yielding of steel reinforcement under pure tensile load. So the force and deformation corresponding to the yielding of steel reinforcement. Kindly take 1 minute. It is straightforward, and it is the procedure is similar to what we did in the previous question.
Option E.
Okay, thank you for the response. We will wait for 30 seconds. If anyone has to wishes to contribute. Okay, so we will go ahead with the the solution, and yeah, as the participant rightly pointed out, it is option E is the correct answer. And again, it is quite straightforward. You have to find out the value corresponding to the yield of steel reinforcement. So P is equal to Fs into As, and yeah, we will write it for the sake of completeness, but once a cracking has occurred, so Fc, this value becomes 0, right? And we have Fs is 500 MPa, that is the yield strength, and As is 3217 mm square. So that gives us a value of 1609 kilonewton, right? And epsilon is equal to 0.002 plus 0.87 Fy by Es. So when you substitute the value as 500 MPa, and when you substitute this value as 2 into 10 to the 5 MPa, you get value of 0.00417 as we saw in the previous problem, and the value of deformation would be epsilon into L, and L is 1000 mm, right? So we get a value of 0.00417 into 1000, that gives us a value of 4.17 mm, right? So these are the final results. I hope you were able to arrive at the right answer. So the correct answer is option E, right? So here we have just tried to plot the force deformation curve. This is what it looks like, and ultimately the comparison between the three columns that we have analyzed in this particular class, right? So again, I have plotted this using the Excel. And one side note is that basically we need to these force deformation curves, these are usually predefined when we are doing analysis and design on commercial packages such as SAP and ETABS. But when we are doing a research problem, when you need to look into a problem with some additional data, so you need to develop these kind of curves and basically analyze, which can actually provide slightly different results when compared to the conventional commercial packages. So if anyone is interested, I'll be happy to share the Excel file with you, and you can actually play around with different members and cross-sectional different columns and their cross-sectional properties and their different force deformation relation. So okay, so we have one more problem. So yeah, I hope that this is fine, because we have exceeded the time limit. I hope we can stay back for another 5 minutes.
Okay, sir.
Yeah, I know today it has been quite long, this session, but my intention was to cover the numerical problems. So with your permission, I will extend the class by another 5 minutes. Yeah, so we will take up the last problem for the day. Thank you for your patience. But this is really important. This question 14, I think it sums up whatever we have learned so far. So I request all of you to kindly be patient and solve this problem. So in the previous question, we found out that the ultimate compressive and tensile strength are 6928 and 1609 kilonewton. If we need to increase the compressive and tensile strength to 8000 and 1800 kilonewton, what should be the revised area of concrete and reinforcing steel? Okay, so this is the question. I would like to just give you 2 minutes, just if you can come up with the approach. If you can tell me the approach, that would be good enough. Then we can solve the problem together, since we have already exceeded the time. So I
First
hope
we get reinforcement.
Yeah, I hope that you got the question right. So if you have understood the problem, then how do we go about solving this? Okay, so the hint is we need to use simultaneous equations.
D, sir.
Okay. Okay, option D. Right. Okay, thank you for the response.
So how you share the Excel sheet?
You can send me a mail so I can, or else I will put
Okay.
it. I will put it in the folder. There is a Google folder where where the NPTEL team is sharing all the the PDF of this live interaction session, and they are sharing the link to the YouTube video also.
Okay. This
Okay.
is solve section. Solve
Yes.
section where it is done there.
Yes. Yes. So I hope that you're
So
able
along
to.
with PDF, Excel also available. Okay.
Yeah. So I hope that you're all able to access the Google Drive. The Google Drive where all the this class YouTube link is there, and the PPT of the.
And there it is given week 1, week 2, week 3 YouTube videos. Then presentation folder is there. Folder link.
Yeah, right,
In
yes,
that excellent PDF. Both you will upload. Okay.
yes, I will upload both of them. Yeah. Okay, so yeah, so the right answer is option D. Yeah. So may I know who answered the question?
Yes, sir.
Okay, so it is Mr. Sharma. Yeah, thank you, sir. So it means that you're solving the you have followed it correctly, and yeah, I'm really glad that you were able to answer that, and just for the benefit of all the participants, I'm going to just give a hint. So yeah, so we need to look at the we have the compressive capacity and we have the tensile capacity. Okay, so we have the equilibrium equation, that is P is equal to Fc into Ac plus Fs into As. Okay, so we have for compression we have 8000 sorry, okay, we have 8000 into 10 to the 3 is equal to Fc is 65, that is the cylinder compressive strength, into Ac plus Fs is 500, that is the yield strength, into As. Okay, so we will keep it aside for 1 minute. Okay, now let us look at the tensile strength. Okay, Okay, so we have 1800 into 10 to the 3, and FC we are going to take it as 0 because we know that once the concrete has cracked, it becomes the resistance becomes 0 completely. That is FC into AC plus Fs into AS. Fs is 500 into AS is unknown. So from this, by solving equation number 2, we get the value of AS is equal to 1800 into 10 to the 3 by 500, which gives us a value of 3600 mm square. Okay, so when you substitute this value in equation number 1, okay, let me use, so when we substitute the value of AS here, okay, we will get the value of AC as 95,384.6 mm square. Okay, I request all the participants to just verify with these values. So we need to compare these values with what we had in the initial question number 10. Okay, so yeah, in question number 10 we need to compare with that. So yeah, excuse me. So AC, let us call this as AC prime and the earlier AC. So that is 95,384.6 divided by 86,783, and AS prime by AS, that is 3600 by 3217. Okay, so we get the value as 1.10. okay, and here we get the value as 1.12. I hope you were able to follow, and I request all of you to just verify that you're also getting these values, not only for this question but also for all of them. Okay, so I think, yeah, with that we will come to a conclusion of today's live interaction session, and I thank you all for joining the session tonight. So if there is any feedback from the participants, I welcome you all. Okay, today was very intense numerical based class, so if there is any suggestion from your side, we can incorporate that in the upcoming weeks. Okay, if not, I thank you all for your patience and attention. So next week we are going to deal with the flexural members. Yes, would you like to add something, Mr. Dev?
Nothing, sir. Just before start of the lecture,
Yes.
can you give us some notes or something so that we can prepare and come to the class?
Okay, so all the problems that I'm solving, that is based on the week's lecture, what professor is teaching. So I hope that you are having access to that PDF. Hello. Hello. Okay, let me just switch to another source. I hope that you are able to access the PDF, right, of the lecture slides. Hello. Hello, am I audible?
His microphone is off, sir, actually.
Okay, I think I need to disconnect and join once again. So yeah, please hold on. Hello. I hope I'm audible right now.
You are audible, sir. Actually, his microphone is off.
Okay. Can you unmute yourself, Mr. Dev?
Yes, sir. Now it is audible.
Yeah. So I think all the PDFs are available. I mean the PPT using which professor is teaching, right?
Yes, sir.
So those PPT is available. So the problem solving session, the live interaction session, is based on that only. Is based on that PDF only. So I request you to.
Okay, I got it, sir. I got it.
Yeah. So I look forward to meeting you all next week.
Yeah,
Sir, actually,
Yeah.
I asked for some exercise problems, actually. Any book
Exercise.
you refer, that also.
Okay, sir. So
Next section you refer on this.
yeah. This was it was based on what sir told. Sir taught in the lecture slides. Yeah. So next class I will try to come up with some more problems.
No, I am asking you exercise problems to our practice, sir.
Okay. For your practice, I think the textbook by Devdas Menon and Pillai, Unikrishnan Pillai.
Okay.
Pillai and Menon. So I think that
That
is
is
good.
sufficient.
Yeah, that is.
Okay.
And if you want additional, you can also refer to Subramaniam.
It's
Okay.
a latest.
Yes. Yeah, latest edition, which is based on limit state design.
Yeah.
So I request you to go through that one. Okay.
So if one book we refer, that will be sufficient, sir, for exam?
Yeah.
Final exam.
For exam, yes, one book is sufficient. So the prescribed textbook is Pillai and Menon. So if you are interested, then from design perspective, I think Subramanian is also excellent book. So yeah, the more the better, sir. But I think these two are more than sufficient.
Okay, this is regarding examination.
Yeah.
So, what type of the examination will be there? Is it a subjective or is a descriptive type?
Okay. So actually, I do not have the exact knowledge because I am working as a TA for the past 1 month only. So I would suggest that you get in touch with the NPTEL team. So I think they will be able to answer your question more precisely.
Okay, the one more thing is that whenever we have the doubt and at the
Yes.
time of the study, we want to clear it
Yeah.
at that moment only.
Yeah.
But unfortunately, we don't have any contact numbers.
Okay.
So,
So
is it possible to get someone's contact numbers?
no. Actually, this live interaction session is scheduled for that only. So whenever you are attending the weekly lecture, if there is any problem, if there is any doubt, so I request you to make a note of it at that time, and you can ask me in this particular session. So I'll be happy to answer, but at that point only to answer it will be difficult. But if you bring any doubts, if you raise any concern during this session, I'll be happy to address that for you.
Okay.
Yeah.
The actual option is given in the NPTEL portal to raise the doubts.
Yeah.
But there is no response actually.
Yeah, I mean, we are all busy actually. Like, if time permits, we do answer them. But like I'll be more than happy if you can bring it to my notice in this class. Like because we are having 2 hours. We can devote a good amount of time for that. So yeah, I mean, please bring to my notice before the next. When we commence the next session, kindly bring it to my notice at the beginning of the class, so that we can answer them.
Sir, what will be the subject for the next session?
Next session it would be flexural members. So the live interaction session is going to follow the same sequence that is being followed in the NPTEL portal.
Okay.
So week 5 and week 6 is flexural members.
Week 5 and 6. Okay. As per the schedule of the NTPL, we have to go along with that. Okay?
Yes.
Got it.
Yeah. Okay.
Okay. Thanks, sir. Thanks
Yeah.
a lot.
Yeah. Thank you so much for joining, and look forward to meeting you all next week. Yeah.
Okay.
Good night. Good night to all of you.
Good night. Good night, sir.